So today we will be continuing our study of arrays. We're going to talk about deep and shallow copying, processing an array, and finally end with partially filled arrays. As you go through this, do all the to-dos just like with the last video. You could answer the questions in a document, and code, you could just turn it in the actual coding part. All the coding part should be done in Eclipse or some online editor. Let's see. There we go. So let's talk once more about deep and shallow copying. And as we do this, I'm going to tell you a memory story. It's a famous story, and you can repeat it, and people will understand what you're talking about. But it may or may not be completely true. Maybe it could be a simplification. But feel free to talk about this story whenever you're talking about computer memory. All right, so let's say I have computer memory and I'm representing it as this stack. And basically the stack I'm referring to is just this white square in the middle of the slide. All right, so the first thing I do is I open Microsoft Word, okay, and Microsoft Word gets loaded into memory, all right? And then I open the Chrome browser, and the Chrome browser gets loaded into memory. So I got Word and Google Chrome running. And then I open Spotify, and Spotify gets loaded into memory. All right, so far this should look pretty normal, or at least match your conceptualization of memory thus far. So right now what I want you to look at, though, is that since Chrome is in the middle of Spotify and Word, Chrome is running and it's boxed in, meaning it has no way to grow, okay? What does that imply? Well, let's first ask the question, does Chrome need the ability to grow in memory while it's running? And I'm going to report to you that the answer to that is an emphatic yes. And if you actually kind of think about it, you can probably come to that conclusion too. I have never seen a Chrome browser with anything less than 9,000 tabs opened. And those tabs don't start all open, typically. What happens is as you use the browser, you keep on adding tabs again and again and again. And each time you add a tab, it takes up more memory for Chrome. So how does Chrome get all this memory? Okay, how do we accommodate this influx of new memory when Google Chrome is clearly boxed in? It can't have any place, it doesn't have any place to grow, right? Microsoft's on top of it, Spotify's on the bottom of it. So what we do is we make sure programs that are currently running have the ability to increase their size while they're running, okay? We call that dynamically. They can dynamically increase their size, okay? And for that reason, this is also referred to, this concept is also referred to as dynamic memory. So here's the dynamic memory story, and that is the stack, which houses static memory, memory that is determined at compile time, grows downward from the top of memory, okay? So the stack is all the memory that we know before we run the program, okay? Things like, you might imagine that if I have an integer, for example, that integer is 4 bytes in Java, we know that. I could show you the code to that, and you could point at that integer and be like, that will take 4 bytes of memory, and you don't have to run the program to determine that, and therefore that could be something that would be stored in stack memory. The heap, on the other hand, also referred to as free store or dynamic memory, is all the memory that is requested by a program at runtime. And we say that this memory grows upward from the bottom of memory. So the stack grows downward and the heap grows upward. Okay. And it's said that when the stack and the heap, if they ever meet, you're out of memory on your system and you can't, your programs, one of your programs needs to close and free its memory. And you might imagine what that looks like on your computer if you've ever had that kind of situation. So each of these programs has access and can request dynamic memory, or as we say, memory and free store, and can link and reference their stack memory to heap memory, allowing them to grow the program at runtime. So what do I mean by that? So Microsoft Word can't grow in the stack, but in its stack memory, it can have a reference or a memory address of heap memory, which is this magical place where it can have additional memory that it needs to request during runtime. Okay, you might imagine that this is something Microsoft Word needs to do because your document is constantly growing in size, right? Especially if you're writing, one day it's 2 pages, the next day it's 10 pages, right? Similarly, Google Chrome has its stack memory, but within its stack memory, it has a reference, a memory address of heap memory where it can grow as big as it needs to grow, okay? Which is necessary to house all our tabs, for example, okay? And we can grow Google Chrome's memory or Microsoft's Word memory or Spotify's memory without having to grow the stack memory, all right, the static memory. So this is static and dynamic memory in Java, and I put a little star there to say for the most part. And you don't have to worry about that star right now. If you understand this story, you'll understand enough to continue on to data structures and succeed. So there's 2 basic types of variables in Java. There are primitive types. Those are a lot of the types we learned at the beginning of Programming 1. Int, double, char, boolean. Primitive memory types start with a lowercase letter. We talked about that. There's static memory. That's something that you might have realized as we went through Python Tutor, but now we're making it explicit. The primitive types are stored on the stack. Okay, they are static memory. We know how big these types are before the program even runs. The size is known at compile time, before runtime. Int is 4 bytes, doubles and 8 bytes, etc., etc. And it holds the value of the variable directly on the stack. We'll see a picture of that in the next slide. In contrast to primitive types, we also have object or reference types. Things like arrays and scanner and strings. Object memory type starts with an uppercase letter, often, okay? It's dynamic memory. It's stored on the heap or the free store, all right? And size can be determined at runtime, all right? So for our array, for example, we can determine its size at runtime, okay? And the way we do that is that we have just a reference on the stack that's referencing memory in the heap, and in the heap, we can have as much memory as we need to hold that particular variable. Okay, so we hold the value of a memory location on the stack that references the variable value, and later we'll call these heap values objects. You might have already noticed that in Python Tutor, they have the frame on one end and objects on the other side, and the frame is our stack and objects are our heap. Okay, we'll call these heap values objects on the heap. Okay, and in Java, dynamic memory is requested by using the new keyword. Okay, so you've used dynamic memory before. You've used the new keyword, and when you use the new keyword, what you're saying is, I want memory on the heap. You're requesting memory on the heap. Okay, and then Java gives you that memory, and that memory has a memory location, and that's what's stored on the stack. So what does this look like in memory? You can see some code down here where I have an integer value x. I have a string that I'm initializing with the new keyword, right? And I have an integer array that I'm also initializing with the new keyword. So when you see these two new keywords, as you might imagine, that means two things are going to exist on the heap. Okay, and notice I've put stack next to the frames in Python Tutor and heap next to the objects in Python Tutor. All right, so x is a primitive variable. It's stored on the stack, and if you look inside x, you'll see the value of the variable directly. Okay, on the other hand, string is stored on the heap, and on the stack we have a reference or the memory address of where we can find that string on the heap. Okay, so by using the new keyword, we're requesting new memory on the heap. Okay, and then our variable stores the address of that memory on the stack. Okay, in this case, we're going to say the address is ID 424. Typically, it would be some hexadecimal value, 0x9273. All right, you might see that when you do C++ next semester. Similarly, our array holds another memory value on the heap. And if we go to that memory value on the heap, we will see that we have enough space to hold 10 different integers, okay? And then that for loop just populates the integers with I plus 43. So the 0th value has the number 43 in it, and the first index has the number 44 in it, etc., etc. Cool. So a quick to-do, after the following code executes, how much memory do we have on the stack and how much memory do we have on the heap? Okay, imagine that to store a memory location takes 8 bytes. That's called a 64-bit system. Okay, so 8 bytes, right? There's 8 bits per byte, so 8 times 8 is 64-bit system, which means every memory address is 64 ones and zeros. Okay. And when I say how much memory do we have on the stack and how much memory do we have on the heap, you can do it in terms of bytes, okay? And so you might think that, well, the stack has a double, an integer, and then these two reference variables, right? My double array and my integer array, okay? And so those must be those must be addresses, right? And then on the heap, we have whatever, 4 double values and 5 or 6 integer values, okay? So we now arrive at the idea of deep and shallow copies, okay? And in primitive world, we don't actually have this idea. Everything is a deep copy in primitive world. So when you're working with static variables, everything's a deep copy, okay? Which is why you've never heard the term deep and shallow copy before. All right, so in this case, we have int x equals 10, all right? And if I say int y equals x, what'll happen is that y will be a copy of x. A copy of x's value is automatically made and put into y, all right? And so we see int y equals x, and the value is copied. So using the assignment operator, which is the equal sign, of course, we can copy a value from x to y. In reference or object variable world, setting two variable references equal to each other using the assignment operator will just copy the memory location over. So it'll do the same thing as saying int y equals x. It just so happens that we don't have the actual value in that for that variable. What the variable's holding is a memory address. So the memory address will be copied over, okay? So what we get in that case is two variables referencing the same memory on the heap, and that is what we call a shallow copy. They're just aliases of each other. In this case, if you look at the code below, we have my array, that's an integer of 10 ints. I mean, that's an array of 10 ints. And we populate it just like we did on the previous slide. And then we create a new integer array called myArrayShallowCopy, but we set it equal to myArray. So what happens is that myArrayShallowCopy and myArray both hold the same memory address, which means they're both referencing the same array in memory. And so we have two reference variables referencing the same exact object in memory, which means that I can make a change to myArrayShallowCopy and it will change the array that myArray is pointing to right now, or referencing. We should say, let's use the reference term. I guess I'll just make a little note of that. I'll sometimes say pointing to, and I'll sometimes say reference. Those two things mean the same thing, but if it seems confusing or if I go back and forth accidentally, please stop me and try to, and if it's confusing, make sure you get it clarified. But those two things are the same thing. I'll try to say referencing. So myArray and myArrayShallowCopy are both referencing the same object in memory, that same array. And so any change we do to myArrayShallowCopy will be reflected in myArray and vice versa. They're the same thing for all intents and purposes. Two different names for the same exact thing. Notice we only have one new being called here, which is a big indication that we only really have one array on the heap. Okay? Because if we had more than one array on the heap, we should be asking for more memory. So both can be used to change the values of the array. They are the same array at this point in time. Notice myArrayShallowCopy of 0 equals 15, right? Remember, everything we can do to an integer, we can do to a single index of our integer array. And so we grab that single index and we assign the value 15 to it. And myArray of 0 now equals 15. So on this to do, I want you to write some code that doubles all the values in myArray without using the reference variable myArray, okay? And then prints out all the values using myArray. So you might create another reference variable and use that to change all the values in myArray by doubling them, and then maybe print those things out using myArray. All right? So your code goes after the for loop there. So now that we've covered the shallow copy, we need to talk about, well, how do we actually do a copy where we have two different objects in memory and one is an actual copy of the other. They're not referring to the same object in memory. And so we have the following. The first thing is we have to ask for new memory on the heap using new. Okay, so if I have an array I want to copy over, in this case, it's myArray, I first have to ask for new memory on the heap using new. And I do that right here. I noticed it's cut off a little bit, but inside the array things, we're just calling myArray.length, and then we close off the array brackets with the ending bracket there. Okay? And so what that does is that gives us an array on the heap that's the same size as myArray. Okay? And then what we do is we copy over the values. Okay? And we do that by just cycling through myArray and setting every index of myArray equal to the index of myArray deep copy. Or I guess I said that the opposite way. Every index of myArray deep copy to the index of myArray. So myArray deep copy of 0 is now going to equal myArray of 0. And myArray deep copy of 1 is now going to equal myArray of 1. right? And you can see that in objects there to the right. So that's number 2. And number 3, by the end, we have 2 arrays on the heap with the same values. Notice that there's 2 different memory locations. My array has ID 424, okay, and my array deep copy has ID 425. But my array deep copy and my array have identical values at this point in time. Note that a change to one array will clearly not change the other, right? You can change my array deep copy without changing my array, and you can change my array without changing my array deep copy. For example, if I said my array of 0 equals 15, like we did in the previous slide, it won't change my array deep copy. Okay. Also note that there are 2 new arrays on the heap, right? So we use new twice, and that's a clue that this is a deep copy because we actually asked for more memory so that we can copy the values in, as opposed to the shallow copy where there was only 1 new, right? And meaning there's only 1 object on the heap. So now we'll do a quick kind of jog into something that involves both a deep copy and a shallow copy, and that is the resizing of an array. All right. So what do I mean by that? Let's say my array has 10 values in it, and at some point we say, well, that's great, but what if I want to insert another value into my array, right? How do I do that? Well, I can't say my array of 10 equals a number because there's not a 10th index in my array initially. All right, there's only 9 indexes in my array, right? Starting at 0 and going to 9. If I do that, what I'll get is I'll get an error in Java because I'm trying to access an index that's out of bounds. So it's called an index out of bounds error, and it will stop my program in its tracks. I highly recommend you try that out. In fact, I should have made that a to-do, so maybe we'll do that in class today. All right, so we have an issue here, right? My array is of size 10, and we want to increase its size, okay? And so the way we do this is we first create a temp array that's bigger than the original, okay? So in the previous example, we made an array that's exactly the same size. Similar to that, we're going to make an array, but we're going to make it twice its size. And typically, that is what we do. We typically make it twice the size. And we'll talk about that. You'll talk about that more in depth in data structures. But you really don't want to do this resizing of the array a lot. So that's sometimes why we end up trying to make it so that we don't have to increase the size of the array over and over again. We'll talk about that later today, actually. I think I'm jumping ahead of myself. So in this case, let's just assume we're making it twice its size. We want to hold double the amount of information or double the amount of integers. Okay, so we have this temp resize array. And then the second thing is we deep copy over all the values from the original to the new array. Okay, so notice we kind of do the same thing as we did in the last slide. Okay. Then the final thing we do is we want to make my array reference the new array that's double the size. And so we say my array equals temp resize array, which is a shallow copy. So we first do the deep copy from my array to temp resize array, and then we do a shallow copy from temp resize array to my array. Okay, think about what that does. By the end of this code, my array and temp resize array are both pointing or both referencing the same memory, which is this array that's double the size. And so we can use my array now and say my array of index 10 equals 500, and we won't get the error. What happened? So sometimes some of you might be wondering, well, what happened to that original array, right? Nothing is referencing it anymore. And what happens is in Java, if nothing is referencing an object on the heap, it'll be freed or garbage collected, meaning it's free memory now and can be used by other programs or other variables in your program, or that ask for heap memory. Okay, it's free. Those values are eventually going to be overwritten by something. Okay, so what you have here is you have my array that's been resized for all intents and purposes, right? And the original array that my array was referencing has been garbage collected and freed. This automatic garbage collection is actually a feature of Java that you will learn to appreciate when you go to C++, and you don't get this automatic garbage collection. And so things are a little different in C++. Okay, so quick to do. How come in the previous code, in the second for loop, we go to myArray.length and not temp resize array.length? So think about that and write your answer in some sort of document. All right, so we will now come to a few processing things that we can do with arrays. All right, in this case, we're gonna look at summing an array and then finding the min and the max. This is review. This is very similar to something we did like gas prices, and we also did something similar in class, but I want you to look at this and really understand it, okay? There might be a new bit of code here that you haven't seen before called a ternary operator, okay? Don't let it throw you off. All it says is that this line will evaluate to the first one if the condition is true, and the second one if the condition is false, all right? So if my min, the right-hand side of this equality, my min equals, right, on line 14, it will evaluate to my min if my min is less than my array of I, and it will evaluate to my array of I if my min is greater or equal to my array of I. Okay? Shouldn't be so complicated. It's just a way to do the if statement in one line. So it's a nifty way. If you have an if statement, right, an if-else statement, which is meant to set a variable, and you don't want to say if this is the case, make my min this, else make my min that, or something like that, right? You can do something like this, which saves you some code and sometimes looks cool. All right. If that doesn't make sense, feel free to use your if branching statement instead. It's the same thing. It's called a ternary operator. It's fun. Okay, so what we've done here is we've created my array, right? And it's referencing some values on the heap. And we go to myArray.length and we populate it with this I plus 43 thing, right? And then we create a sum, all right? And we initialize my min to the first value of the array, and we initialize my max to the first value of the array. Okay? And that's a very common thing, to try to initialize these things to actual values, right? This is a valid value to initialize it to. If you try to initialize my min to 0, all right, then you might just get out a value of 0. Some of you were doing that. Some of you did this thing that was initialize my min to the maximum integer. And there's actually a way you can get that by using integer.maxint, right? Or something like that. I always have to look it up. But that's a way that's a very Java specific way. And I want you to use a way that's more globally usable in other languages, for example. And so the smarter thing to do is to set it to a valid value, which is the 0th value, okay? And then we can go through this whole thing and we can add up, we can sum these things up, and then we can check if there's a value that's smaller and than my min, and we can check if there's a value that's bigger than my max, right? If my array is bigger than my max, then this thing is going to evaluate. My max will now be equal to my array of I, okay? And this should find the minimum, maximum, and the sum of this thing. You can print it out at the end if you want. I have a to-do here, and the to-do is to update the previous code to initialize sum to my array of 0. How would the for loop bounds change in that case? Okay, so some of you might have said, wait, we're initializing my min to my array of 0 and my max to my array of 0. Why don't we initialize my sum to my array of 0 too? I mean, it's just as valid, right? The first value is going to have to be used in the sum anyway, so why don't we just do that? And if you do that, you can change the for loop bounds. And so how would you change the for loop bounds? The final thing I want to talk about today is partially filled arrays, okay? So we will learn in data structures that resizing arrays is time intensive. Therefore, we don't necessarily want to do it often. So instead of resizing all the time, we can do something called a partially filled array. What is a partially filled array? Well, a partially filled array is an array that isn't completely filled, and so if you add values to it, you can do it pretty quickly. You don't have to resize it because it's still got spaces. It's got empty spaces in it. So you can think of it as an array with empty spaces, okay? The way we accomplish this is we use a variable named count to keep track of the number of values in the array, okay? Right now, you can see this little array at the bottom I have, and count is equal to 0. Count will also coincidentally keep track of the next index we insert into. So count equals 0, our partially filled array is empty, all right? And 0, coincidentally, is the next index we insert into. So if I had my array, I could say my array of count equals something, right? And that would insert the value into the 0th index of my array. Once we insert in, we add 1 to count. Okay, so every time we insert, we add 1 to count. That makes sense. We insert into the array. Now we have one value in the array, and we add 1 to count. We resize our array. Typically, we double the size, as we talked about earlier, if count equals the array length. Okay, in this case, we've got to resize the array when count ends up being 4, right? Because that's the array length. So we go from count 0 to count equals 1 to count equals 2 to count equals 3, right? To count equals, 5. 0, 1, 1, 2, 3, 4, 5. Yes, when count equals the array length. So we can insert into 4, right? And then count's going to come over here, and count's going to equal 5, and that's when we need to resize this thing. When count equals the array length. And in this case, the array length is 5. Sorry, I miscounted. So count equals 0. That's the first place we're going to insert into. And we insert the number 3. So you might imagine that's my array of count equals 3, right? And then count equals 1 at that point. And then we wait for the next insert. And when that happens, we're inserting at that index. And then count equals 2. And then we insert whatever at that index, right? So if someone says they want to insert the number 12 there, for example, we can do that. And we do this all the way up until count equals the array length, and then we have to resize this thing, okay? And then typically we resize it as double, and then we keep count going, right? So count will equal 5 at that point, we'll insert into 5, count will equal 6, we'll insert into 6, until count equals 10 at that point, right? It's a bigger array now, and then maybe we resize it to 20. So we have a final to do. Okay. What I want you to do is I want you to use a partially filled array called test scores with a count variable. Populate test scores using a while loop where you ask the user to input a test score and save it in the array. Make the initial array length 4. If you run out of space in the array, resize the array in the while loop before continuing. Okay, so the user's going to input values like 95.2, 93.1, 96.8. You know, this is a really, really good student getting all 90s, right? And you're going to add that to this array test scores, right? Keeping in mind that, you know, if they added more than 4 test scores, then our count's going to equal 4, and we have to resize this thing. So it says, if you run out of space in the array, resize the array in the while loop before continuing. Okay. When the user inputs any negative number, exit the while loop. So we're going to assume that the negative number is our cue that the user doesn't want to input anything else, right? And so they input some random negative number, and you just exit the while loop. Then use a for loop to process the loop and output the minimum test score, the maximum test score, and the average test score. Keep in mind that when you go through this for loop, you don't necessarily want to go through the whole length of the array, because this thing is a partially filled array. That means some of the values it has in it are gibberish, right? Because it might not be filled all the way. So instead of going to the length of the array, what other number might you go to, right? What number signifies how many actual values are in that array? Think about that and use that as your bounds on your for loop, all right? Then use a for loop to process the loop and output the minimum test score, the maximum test score, and the average test score. Okay, this is very similar to the previous slide. In fact, maybe this is a good way to practice the use of the ternary operator for the min and the max. All right. Finally, I want you to test the program with 3 tests and 5 tests, right? Make sure you test the resize is basically what I'm saying. And then, you know, you could even test it with something greater than 8 if you resize it to 8 to make sure 2 resizes work, things like that. If you're having trouble with that, please contact me, please talk to me. This particular part of the assignment is something that's very akin to something we will do in data structures called the bag class. Okay, and it is you're one of your first data structures. And so if you know how to do this, you will know how to do the bag class, and you will be ahead of the game when you get to data structures. All right, that's all I have for you. So get started early, and I will see you online or at office hours if you have any questions.